I have in my hand a rock. But it is not just a rock. It is a record, a journal that tells us the story of our beginnings. It is a tangible piece of space, and in many ways, a piece of time. I'm holding a fragment of the meteorite called Allende. It is a fossil from the formation of the solar system and represents one of the very few ways we have to look into the past in an effort to understand how the Earth and the other planets came to be. Every single person shares a history that is told by this rock. If we slice open the meteorite, we see that it is made of many small pieces of rocky minerals, of some glassy material, of some metal. What tend to jump out at the eye are the small spherical objects. These are chondrules. They are 0.1 to 1 millimeter in size and found in high abundances in a common class of meteorites called chondrites. Meteorites, such as this, come from asteroids that never melted completely. And this is fortuitous, because complete melting, which did happen in many cases, would have largely erased, if not completely, the details of how the material came together to form the asteroid. Every single one of these chondrules contains information about when and where they formed and the conditions in which the planets themselves were built. Some meteorites with chondrules such as this even contain material that may have been necessary for promoting life on Earth. But buried in all of these potential answers is a staggering problem. We do not know how the planets formed. The issue is that the asteroids, along with comets, are fundamental building blocks of planet formation. We call them planetesimals. The problem is that we do not know how the planetesimals formed, means we do not know how the planets themselves formed. Here's the general picture as we know it. To build a planet, these very small grains from the previous generations of stars must come together in the swirling disk of gas and dust and grow from micrometer sizes to the gargantuan scales of planets with diameters of 10,000 kilometers or more. The dust needs to grow to become over 1 trillion times larger. This proceeds easily at first, with grains sticking due to electromagnetic effects. Mechanical sticking aids this process, just becoming tangled and twisted as the dust develops complex structure. Eventually, though, the grains grow to the scale of sand and small pebbles. And this is the heart of the problem. These grains of sand and small pebbles tend to bounce off each other or break apart rather than grow. In fact, there are many different physical processes that we can think of that seem to prevent the formation of the planet-building asteroids from the chondrule-size objects. We don't know how to go from the scale of sand to the scale of a city in planet formation. This takes me back to this rock. Chondrules are primitive objects from the solar system's birth. Their size corresponds to the same size that appears to be frustrated in the growth toward planets. Chondrules in their asteroids are a physical manifestation of the crevasse in our knowledge of planet formation. Although they were incorporated into the asteroids through processes we simply do not understand, once there, they were preserved for billions of years, allowing us to study them today. They are a piece of time and a piece of our beginnings. My work, in part, explores the types of events that could have turned dust aggregates into the beautiful minerals seen in this meteorite. Why were the chondrules produced in such high abundances? What led to their formation? And how were they incorporated into the asteroids? The answer is here, in this piece of time. We just need to learn how to read the story.